Hello everyone. The previous class we were discussing the revision of gaseous state, that is gas laws and ideal gas equation. So today we continue with the same thing. Okay. So after Charles law, next law is what now here? Pressure law. Pressure temperature law actually. What is this called? Pressure temperature law we say. What is this called? Pressure temperature law. So pressure temperature law is also called what? Gay-Lussac's law. What is it called? Gay-Lussac's law. So Gay-Lussac's law or pressure temperature law we say. So Gay-Lussac's law or pressure temperature law, or we say Charles law 2. What is it called? Charles law 2 also we can say. So Charles law 2, otherwise Gay-Lussac's law or pressure temperature law we say. So here we take what? Constant volume condition. So at constant volume, the pressure of a given amount of gas, the pressure of a given mass of gas varies directly, means is directly proportional to its absolute temperature. Means what now here? When temperature of the gas increases, the pressure of the gas also increases. In general, the pressure of gas is due to what? The collisions of the gas molecules on the walls of container. Okay, there will be collisions among the gas molecules also. So one gas molecule collides with the other gas molecule. That will not exert the pressure because the molecular collisions will be elastic in nature. But when the molecules collide the walls of container, the gas exerts what? Pressure. So the pressure of gas increases when temperature of the gas increases. So that point we have to understand. So pressure is directly proportional to what now here? Absolute temperature. Where capital T indicates what? Absolute temperature, Kelvin temperature. So when you take this one here, P is equal to what now? Some constant K into T. So P is proportional to T now, then P is equal to some constant K into T, proportionally constant K. Then what we take now? P by T is equal to constant. P by T is equal to what now here? Constant. So the same thing we can take. P by T is equal to constant. So P by T is equal to constant. Therefore, initial conditions if you take and final condition if you take, it is P1 V1 initial condition, P2 V2 final condition suppose. Then P1 by T1 initially is equal to what? P2 by T2 finally. That means what now here? The ratio of P1 to T1 initial is equal to what? The ratio of P2 to T2. So P1 by T1 is equal to what? P2 by T2. This is important equation for Gay-Lussac's law or Charles law 2 or pressure temperature law. So this point. The same equation how to write? Tell me. P1 by P2. We have taken this P to this side. P1 by P2 is equal to what now here? T1 by T2. T1 by T2. So P1 by P2 is equal to what? T1 by T2. So P1 by P2 is equal to T1 by T2 means what? Pressure is directly proportional to temperature. So this is called Gay-Lussac's law. Is that clear? Take the screenshot of this. So at constant volume, whenever we keep the volume constant, at constant volume, if you draw any graph, if you plot a graph, that is called what now here? Isochore. Isochore means what? Graph plotted at constant volume. At constant volume, if the graph is plotted, which is called isochore. Isochore. At constant pressure, the graph is called what? Isobar. Isobar is what? At constant pressure. And isotherm. Isotherm is what? The graph at constant temperature. Therm means what? Thermal. Indicates what? Temperature. Isotherm indicates what? Same temperature. When temperature is same initially and finally. That is, when temperature is constant. The graph plot is called what? Isothermal graph. That is in case of what? Boyle's law. The graphs of Boyle's law are called isotherms. And the graphs of Charles law. In Charles law, volume is directly proportional to temperature at constant pressure, right? So at constant pressure, the graph is called what? Isobar. So isobaric graphs means what? The graphs plotted at constant pressure. And isochore means what here? The graphs plotted at constant volume. So isochoric graphs we observe in Gay-Lussac's law, isobaric graphs in case of Charles law 1, and isothermal graphs in Boyle's law. So this point we have to keep in mind. Next, gas equation. Gas equation means we say here combined gas law equation. What is called? Combined gas law equation. So combined gas law equation this is. So PV by T is equal to constant. Then initially, finally, if you take what we write, P1 V1 by T1 initially is equal to what? P2 V2 by T2. This is called combined gas law equation. P1 V1 divided by T1 is equal to P2 V2 upon T2. So this is called combined gas law equation. So because PV by T is equal to constant here. Is that clear now? So now see, for 1 mole of an ideal gas, if you take 1 mole of ideal gas here, 1 mole indicates number of moles, how many? 1. Number of moles, we have taken 1 mole. So for 1 mole of an ideal gas, PV is equal to what? 1 into RT. 1 into RT. 1 mole now we have taken here, 1 into RT. If you take n number of moles, for n moles of an ideal gas, PV is equal to n into RT. PV is equal to n into RT here. Is that clear? So from this equation here, what we can take now here, PV is equal to constant into temperature. Na? PV is equal to what? Some constant into temperature. That constant is what? R. Okay, PV is equal to T into constant. This constant is nothing but R. Okay, so that's why we take what now here, PV is equal to 1 RT. So this constant is nothing but what now? R, capital R. PV by T is equal to capital R. Then PV is equal to TR. PV is equal to RT for 1 mole. PV is equal to nRT for n number of moles. If we take 10 moles of gas, what will be equation here? PV is equal to 10 into RT. Okay, so in this way we have to understand what now the ideal gas equation. Okay, next, for W grams of the gas, here we are taking what now? Weight, mass of the gas. So for W grams of the what? For W grams of the gas means what now here? When you take the mass of the gas, W grams. So it is what now? Mass. So mass of gas we have taken how much here? W grams. In that case, what here? PV is equal to nRT. In place of n, what we are writing here? Mass by gram molecular mass. So number of moles is equal to what? Given mass divided by gram molecular mass. So mass by molecular mass into RT. Where here we are taking V this side. V volume we are taking on the right hand side here. Then P is equal to W by M is already there here. W by VM. W by VM. So W by VM into RT. W by VM into RT. Where W by V is what now? Mass by volume now. Mass by volume is nothing but density. Mass by volume is what? Density. Did you understand this step here? This step did you understand? PV is equal to W by M RT. W is what your weight or mass. Mass by molecular mass. Na? So again, here V volume is taken to the right side here. So V has come to the denominator of right hand side. Then P is equal to W already there here. WRT already there by M is there already here. So WRT by VM. WRT by VM is what now here? P. P is what now? Pressure. Is that clear? Now mass by volume. This mass by volume is nothing but density here. So mass by volume into RT by M. So this is what now here? P. Formula for P. Pressure of gas. So pressure of a given gas is calculated by the formula dRT by M. Small d RT by M. Here pressure is taken about generally ATM. Pressure in atmospheres, and the density will be taken in grams per ml. So grams per ml or grams per cc. Cc means cubic centimeter. 1 cubic centimeter, 1 centimeter cube is equal to 1 ml, remember. So 1 gram per ml. So generally density is taken in gram per ml or cc, gram per cc. And R is what now generally? R is in liter atmospheres. R is to be taken in liter atmosphere, 0.0821 liter atmospheres. Kelvin inverse, mole inverse. And T, temperature should be taken in what now? Kelvin. Kelvin temperature. Kelvin temperature we have to take. If centigrade temperature is given, we have to convert into Kelvin temperature by adding what? 273 value. 273.15 actually. 273.15 to be added to given centigrade temperature to get Kelvin temperature. And M is what now? Gram molecular mass. So the molecular mass in grams we take. If you take oxygen gas, O2 gas, 32 grams. If you take nitrogen gas, 28 grams. If you take CO2 gas, 44 grams. So like this, gram molecular weight is M, capital M. Right? Let's take the screenshot of this. Yeah. So next. So what is R here? R is called universal gas constant. That means what? Why we said universal here? Because it is same for all the gases. This R value is same for all the gases. Okay. It is expressed in the units of work per degree Kelvin per mole. So work done by the gas by what here? Degree Kelvin means Kelvin temperature and per mole. Per 1 mole per 1 Kelvin. So per Kelvin per mole we take here. Is that clear now? So here work done by the gas divided by temperature into mole, number of moles. So this is the what your formula. Generally we know that PV is equal to nRT, right? From this R is equal to what now? R is equal to PV by NT, right now? So here PV is nothing but work done. PV is nothing but P into V is nothing but the work done. So the work done by the gas is equal to what generally? Pressure into volume. Pressure of the gas exerted. Pressure exerted by the gas into volume of the gas. Will give this product will give work done by the gas. Divided by Kelvin. Capital T is Kelvin temperature. Small n is mole. So like this work done divided by mole Kelvin. This will be units of R. Okay. So value of R, numerical value of R in different units can be given like this. So first R is equal to what now? In liter atmospheres. In liter atmospheres, it will be 0.0821. 0.0821 liter atmospheres, Kelvin inverse, mole inverse. So this will be same for all numerical values. For all types of numerical values of R, K inverse, mole inverse will be common. So here, K inverse, mole inverse. Kelvin inverse, mole inverse. This will be same for all. Next, check it here. Suppose if the work done is taken in liter atmospheres, if the work done by the gas is taken in liter atmosphere means P into V na volume in liters, pressure in atmospheres. If you take pressure in atmosphere, volume in liters, so liter into atmospheres, that will be work done by the gas. So what we have to remember is that, so 1 liter atmosphere, 1 liter atmosphere, 1 liter atmosphere of the gas is equal to 101.3 joules. We have to take this conversion, we have to remember. So 1 liter atmosphere means 1 liter of the gas if it exerts 1 atm pressure. If 1 liter of gas exerts 1 atm pressure, in that condition, what will be the work done by the gas? How many joules of work will be done? 101.3 joules work is done. Remember. Is that clear, ma? That is equal to what now here? 101.3 into 10 power minus 3 kilojoules. Because 1 joule is equal to what now? 10 power minus 3 kilojoules. Or 1 kilojoule is equal to 10 power 3 joules, na? Then 1 joule is equal to 10 power minus 3 kilojoules. Right? So 1 kilojoule is equal to, kilo means how much? 1000. 10 power 3 joules. Then 1 joule is equal to 10 power minus 3 kilojoules. So in place of joule, what we can write here? 10 power minus 3 kilojoules. So this is what now the work done by 1 liter of gas when it exerts 1 atm pressure. So this conversion value we have to remember. So 1 liter atmosphere is equal to 101 point. This remember mainly remember this value. 1 liter atmosphere is equal to what, ma? 101.3 joules. Okay. So R value in liter atmospheres, how much it is? 0.0821. And R value in milliliter atmosphere. Milliliters atmosphere. So 1 liter is equal to how many milliliters? Tell me. 1 liter is equal to how many milliliters? 1000, na? So 1000 milliliters we write. In place of 1 liter, what we write? 1000 milliliters, right? So here in place of liter, what we can write here? 10 power 3. 10 power 3 indicates what? 1000. So 1, 2, 3, 82.1. So 82.1 milliliter atmosphere, Kelvin inverse, mole inverse. Sometimes in bits they may ask you. So R value in milliliters, atmospheres. Just we are converting liter into milliliters. That's all. Next, 8.314 into 10 power 7 ergs. Here 8.314 joules we know. 8.314 joules. How we got this joules here? By taking what? 1 liter atmosphere is equal to 101.3. In place of liter atmosphere, if you take 101.3 joules, we get 8.314 joules. And 1 joule equals to 10 power 7 erg, no? 1 joule equals to 10 power 7 ergs. That's why 8.314 joules we can take, or 8.314 into 10 power 7 ergs. Okay. Or in calories we can take, in calories. 1 joule equals to how many calories? 1 by 4.2. So 1 joule equals to 1 divided by 4.2 calories, because 1 calorie is equal to 4.2 joules. 1 calorie equals to 4.2 joules, or 1 joule equals to 1 by 4.2 calories. So like that here, this in place of joule, what we can write? 1 by 4.2 means 8.314 by 4.2 will give 1.987 calories. 1.987 calories or 2 calories. Approximately we can take a round of 2 calories. 1.987 we can round off to 2 calories. So 2 calories work is done. Here 8.314 joules work is done by the gas. Here 8.314 into 10 power 7 ergs work is done by the gas. Here 82.1 milliliters atmosphere work is done by the gas. Here 0.0821 liter atmosphere work is done by the gas per Kelvin and per mole. So these are numerical values of what? R. Let's take the screenshot of this now. Now, next one is what? Now, next another important law is what? Avogadros law. Avogadros law. Scientist name is what? Avogadro. So it is what now here? Under similar conditions of temperature and volume, equal volumes of all gases contain equal number of molecules and equal number of moles. Equal number of molecules, otherwise equal number of moles. Okay, so equal volumes of all gases contain equal number of molecules or equal number of moles under similar conditions of what? Temperature and pressure. Under similar conditions of temperature and pressure, all the gases contain equal volumes of all the gases contain equal number of moles and equal number of molecules. That means what now? Volume of gas is directly proportional to number of moles. And also volume of gas is directly proportional to number of molecules. So more the number of moles, more will be volume. If more volume is taken, more will be number of moles and more will be number of molecules. Suppose 22.4 liters CO2 is equal how many moles ma? 1 mole. 1 mole means how many molecules? 6.023 into 10 to the power of 23 molecules. Right? So 22.4 liters of CO2 is equal to what now? 1 mole of CO2. And how many molecules? 6.023 into 10 to the power of 23 molecules. This number is called what? Avogadros number. If you take CO2, 1 mole like this, 22.4 liters. If you take same volume of N2 gas, nitrogen gas, same volume, 22.4 liters of nitrogen gas, if you take, that also contains what? Same number of moles, 1 mole and same number of molecules, 6.023 into 10 power 23 molecules. There is no change in number of moles and number of molecules if you take same volume. Under what? Similar conditions of temperature and pressure. We say at STP, we say here. STP means what? Standard temperature and pressure. At STP, 22.4 liters of N2 gas is equal to 1 mole. At STP, 22.4 liters of CO2 gas is also equal to 1 mole. At STP, 22.4 liters of any gas is equal to 1 mole of gas. 1 mole of gas always contains about 6.023 into 10 to the power of 23 molecules, right? So this number is called Avogadros number. Avogadros number. Okay. So this is Avogadros law. What is Avogadros law here? Avogadros law states that equal volumes of all gases contain equal number of moles and equal number of molecules under similar conditions of temperature and pressure. So to take similar conditions of temperature and pressure, what we are taking here, STP we are taking. If you take SCATP, what I told you, SCATP, in SCATP, what is temperature? Temperature is equal to 25 degrees Celsius. 25 degrees Celsius means what? Plus 273 is equal to 298 Kelvin. 298 Kelvin. So 298 Kelvin is what? Standard ambient temperature. SCATP means ambient. AMBIENT. Standard ambient temperature and pressure means standard ambient temperature. How much here? 25 degrees Celsius. That is room temperature. 25 degrees Celsius means 25 plus 273. That is 298 Kelvin. Okay. And standard pressure means again 1 bar. Here STP pressure 1 bar. SCATP pressure also 1 bar. STP pressure 1 bar. SCATP also 1 bar. Pressure is same for both cases. In case of STP, what is temperature? 273, 0 degrees Celsius. 0 degrees Celsius means 273 Kelvin. But in case of SCATP, what is temperature? 25 degrees Celsius. That is 298 Kelvin. So this difference here to understand. So if you take same temperature and same pressure for any gas, equal volumes of all gases contain equal number of moles and equal number of molecules. This is called Avogadros law. Is that clear, ma'am? Take the screenshot. I will erase it. So next now, Dalton's law of partial pressures. Dalton's law of partial pressures. Okay, ma? See here now. In this case, the total pressure, P total, the total pressure exerted by a mixture of gases. Which gases here? Mixture of non-reacting gases. Mixture of non-reacting gases. So mixture of which gases we have take here? Non-reacting gases we have take here. Okay, so pressure exerted by a mixture of non-reacting gases, okay, is equal to, the pressure is equal to the sum of their individual pressures, means partial pressures, sum of the partial pressures. Is that clear? You're already given here non-reacting gases concept. So the total pressure P total exerted by a mixture of gases which do not react chemically. The gases should not react with each other. So which do not react chemically is the total pressure is equal to the sum of their individual pressures, that is sum of partial pressures under similar conditions of temperature. Under similar conditions of temperature means what? Constant temperature. Constant temperature means what? Isothermal condition. Okay, what is constant here? Constant temperature. Temperature is constant in this case. Is that clear? So constant temperature we have taken, right? So yeah, P total of gaseous mixture is equal to what, ma'am? Partial pressure of first gas plus partial pressure of second gas plus partial pressure of third gas, and so on. So if you take three gases partial pressures we take here. P1 plus P2 plus P3 is equal to P total. And if you take only partial pressure of any gas, suppose if you want to calculate P1, partial pressure of a gas, suppose we are calculating P1 here. That is partial pressure of first gas is equal to mole fraction of first gas into total pressure of the gaseous mixture. Total pressure of the gaseous mixture. Total pressure of the gaseous mixture we take here. So mole fraction of that individual gas into total pressure of the gaseous mixture will give what? Will give the partial pressure of that individual gas. So partial pressure of any gas is equal to the product means into here multiplication. So the partial pressure of any gas is equal to the product of mole fraction of that gas and total pressure of the gaseous mixture. So mole fraction of a particular gas into total pressure of the gaseous mixture will give partial pressure of CO2. Imagine suppose here I'm taking partial pressure of CO2 gas. Partial pressure which gas? CO2 gas is equal to what now here? Mole fraction of CO2 into total pressure of gaseous mixture. Okay. So if you take air, in air, what will be gases available? Nitrogen gas, oxygen gas, and CO2 gas. If you take the different gases of air now here, partial pressure of only CO2, partial pressure of CO2 is equal to mole fraction of CO2 in the air into total pressure of the gaseous mixture. So this product gives what now here? Partial pressure of any gas. So this is what Dalton's law of partial pressures. So you know that already we have discussed all the gas laws. It is only the revision class. We are revising the important concepts of each and every law. Okay. Yeah. And next one is what now here? Graham's law of diffusion. Graham's law of diffusion, or what we take another word, effusion. The sudden escape of the gas through small holes, small orifice is called what? Effusion. The intermixing of two gases is called diffusion. Intermixing of two or more gases uniformly is called what? Diffusion. Effusion means what? The sudden escape of a gas through small orifice, through small hole is called what? Effusion. So the Graham's law is meant for diffusion as well as effusion. Okay, Graham's law of diffusion. The property of gases to mix with each other to form homogeneous mixture irrespective of gravity is called what? Diffusion. If you open the two gases here, so gas 1 and gas 2. If you open the two gases in the same room, we have opened the bottles of two gases. Now both gases will diffuse now. Both gases will diffuse in opposite directions, and they will be mixing each other here. They will mix with each other. So intermixing of two or more gases to form homogeneous mixture. After some time, the total room is homogeneously. Homogeneously means what now here? Uniformly filled with both gases. Okay, so gas 1 molecules and gas 2 molecules homogeneously occupy the total volume of the gas of the room. Okay, in the room, both gases will be uniformly occupying. That means what? The intermixing of two or more gases to form homogeneous mixture. To form homogeneous mixture, irrespective of what gravity means, when gas molecules are moving, they will not experience any gravity. They will not experience any gravity because each gas molecule is having very small mass. Very less mass will be there for each gas molecule. Okay, suppose you take nitrogen gas molecule. One nitrogen gas molecule is equal to 28 AMU. AMU means atomic mass unit, unified mass. AMU indicates what? Unified mass. So one AMU is equal to what now? Very less in mass. So 28 into 1.66 into 10 to the power of minus 20, 24 grams, minus 24 grams. So it is very small value, 10 to the power of minus 24. So 1.66 into 10 to the power of minus 24 grams is 1 AMU. So 28 into AMU. This is very smaller value. So the mass of each gas molecule is very less. That's why the molecules of gases do not experience any gravitational attraction towards Earth. That's why irrespective of gravity, these two gas molecules will be intermixing with each other. Suppose you take here O2 gas and N2 gas. All the gas molecules will be mixing with each other to form homogeneous mixture, irrespective of what gravity. That phenomena is called what? Intermixing phenomena is called what? Diffusion. And effusion is a special case of diffusion. What is special case of what? Effusion is a special case of diffusion in which, in effusion process, gas passes through a small aperture, small orifice. Orifice means what here? Small hole. Through small aperture, through small hole, what happens now? The gas will escape. This sudden escape of the gas through small aperture is called what? Effusion. So effusion is a special case of diffusion. Is that clear? Now, see here. Under similar conditions of temperature and pressure, means when temperature is constant and pressure is constant, the relative rates of diffusion, the rates of diffusion of gases are inversely proportional to the square root of their densities, and also inversely proportional to the square root of vapor densities, and also inversely proportional to molecular masses. This is called Graham's law of diffusion. So Graham's law of diffusion states what, ma? Under similar conditions of temperature and pressure, the rates of diffusion of all gases are inversely proportional to the square root of density, square root of vapor density, square root of gram molecular mass. So this is called Graham's law of diffusion. Is that clear, ma? So rate of diffusion of first gas by rate of diffusion of second gas is equal to under root density of second gas divided by density of first gas. That equals to square root of VD2 by VD1. VD is what? No, vapor density. That equals to under root M2 by M1. M2 is what? Gram molecular mass of second gas by gram molecular mass of first gas. So this relation we have to understand. Okay. Once take the screenshot, I will erase it. Now what I gave equation for all the gases here, R1 by R2 is equal to under root D2 by D1 we can take, that equals to under root VD2 by VD1, that equals to under root M2 by M1. Here to overall equation what we can take now here, R1 by R2 is equal to P1 by P2, P1 by P2, pressure of first gas by pressure of second gas into under root T1 by T2, under root T1 by T2, under root M2 by M1. Okay, so here what now? R1 by R2, rate of diffusion of first gas by rate of diffusion of second gas is equal to pressure of first gas by pressure of second gas into under root means square root of temperature of first gas by temperature of second gas, and under root molecular mass of second gas by molecular mass of first gas. So this way R1 by R2, the ratio of rates of diffusions we have to understand. Is that clear? Now again, R1 is equal to what? In place of R1, what we can write? The volume of first gas diffused by time taken by first gas. The volume in milliliters, the volume of gas diffused in milliliters, time in seconds. You take it. So rate of diffusion of first gas is equal to what, ma? V1 by T1. If you take second gas, it will be, if you take second gas, rate of diffusion of second gas is equal to V2 by T2. V2 by T2. So like this, the rate of diffusion is equal to volume of the gas diffused by time taken by the gas to diffuse. Is that clear, ma? So the rate of diffusion of volume is called what now here? This. And also now you see. And also what we have to understand is that the same formula, we can take what now here, the rate of diffusion can also be taken in terms of number of moles. Suppose in some cases, number of moles will be given. R1 is equal to what now here? Number of moles of first gas by time taken by first gas. Number of moles of first gas by time taken in seconds. Will be also giving what? R1. And R2 is equal to what now? N2 by T2. N2 by T2. Like this, R is nothing but number of moles diffused by time taken. Number of moles diffused by time taken. So R1 by R2 is equal to P1 by P2 into under root T1 M2 by T2 M1. So this formula will be useful for almost all types of numerical problems. Okay, ma. So this formula is very important to understand. Okay. Take the screenshot of this and prepare well without wasting time.